Hey everybody, it's a beautiful day outside. Let's take a look at this assignment you're going to be doing. Today I'm going to show you how to do some frame analysis, stress analysis using Inventor. And so this is the document that you're going to end up using for this. So you're going to want to have your engineering notebook out so you can add a little bit of notes onto this as I explain some of these pieces. And the part that you're actually going to analyze is this one right here. This is called an engine mount. At least that's what we're calling it. So we have this flat plate at the back. This flat plate is called the firewall, and the engine mounts onto 1, 2, 3 points, and then you would have the propeller out here. And so the pilot would sit back here, and that's why there's the firewall here to protect the pilot. So 1, 2, 3 spots that we bolt the engine to. And as this plane is flying, and tilting up and down and doing all sorts of maneuvers, depending on what kind of aircraft it is, then it's going to experience different kinds of stresses. These tubes, these pipes that are on here that are connecting to the firewall from the engine mounts here are going to experience stress. And we want to make sure that they don't break when we are diving or when we are climbing. They're going to experience some stress, and we want to make sure they're strong enough. So we're going to do the analysis in Inventor to check that out. So we're going to test 3 different materials. We are going to test mild steel, titanium, and aluminum under 3 different conditions: 1G, 6G, and 6G is just under the threshold of when you would black out. Blacking out would be all the blood running from your head because all the force is pulling back and pushing all that blood into your legs. Fighter pilots have flight suits, compression pants that actually help them squeeze their legs and keep that blood back up into the heart and into the brain. So they can do, and with practice, more G's in this. Negative G's is when you are diving really rapidly. All the blood would go to your head. It's a lot harder to control that situation. So it's a smaller value that you can actually retain consciousness. So we're going to set that condition at minus 3G. And we're going to see if those that tubing, that steel tubing in this first case, will hold up or if it will break. And so the first thing that you're going to do is record the effective weight of a 300-pound engine. If we have 100 pounds on each mount, 1, 2, 300 pounds, if we say that's an even distribution just for this purposes of this exercise, then the total weight is 300 pounds under 1G. If you're under 6G, you have to figure out what would the total weight of that engine be if it's experiencing 6G. What we're going to determine is the normal stress on those engine mounts in KSI, which is 1,000 pounds per square inch. So rather than doing it in pounds per square inch, since the values we're using can get quite large, we do it in 1,000 pounds per square inch, or KSI. Now, the ultimate tensile strength for steel is 54 KSI, or 54,000 pounds per square inch, before it undergoes deformation. So take a look at this plastic rod. This is what you're going to want to note. There is this thing called elastic deformation. And elastic deformation is, if I apply a stress to this, up to a certain point, it will always bend back. It snaps back and regains its original shape. We are experiencing elastic deformation. If I take it and I apply enough pressure to this thing and it bends permanently, now it's undergone plastic deformation. So you have elastic deformation, it returns to its original position. Plastic deformation, it's permanently deformed. Permanently deformed aircraft engine mounts is a bad thing. So that's what we're going to be testing. We want to make sure that the stresses that we apply are less than 54 KSI. If we exceed 54 KSI, those engine mount bars are permanently bent, and that means that our whole engine propeller has dipped or changed or broken through the actual fiberglass outer casing. Something extremely bad has happened. All right, so those are the things that we're going to be testing for. Are we less than this ultimate tensile strength where plastic deformation occurs? So to actually calculate normal stress, let me show you how to do that in Inventor. You can maybe do your very first one. If you go the first row all the way across, then you'll be able to repeat it for different materials. So right now we are in mild steel, and that's how I'm giving you the part. I'm going to not even show you how to change that quite yet because I want to do our first analysis. So we go to Design, Frame Analysis, and we right-click Gravity, and then edit that. And we want to make sure that we have all of our values correct here. If I want to do negative 3Gs, I do 3 times this value and flip the load direction. So you see this arrow here, it is now pointing up. That means that it's negative G's. You don't put a negative in front of the 3 here. So that would be negative 3 G's. If I want 6 G's, I reverse it, and I make this a 6. I don't want either one of those. I want 1 G, so I'm going to leave it like that. Oftentimes, Inventor will use 385.827 if you hover over that, inches per second squared. I'm doing it meters per second squared because I like it. All right, I'm going to hit OK. So now we have that applied stress. We have all of these points are fixed, and we have 100 pounds on each end here. So you don't need to change those forces. We're going to simulate this. So once we've adjusted our gravity, we can hit simulate, cancel that little solver message, and we're going to open up the normal stress. So double click that, and you can see the normal stress. So under 1G, I'm getting a 0.4765 KSI. So I go back to here, 0.4765. So that is my actual value for this. Next, we're going to take a look at the safety factor, and that is how many times stronger the tensile strength is than the applied stress. How many times more force can I have than that one load condition there? So if I take this, I can say that's equal to tensile strength divided by stress, and I get 113 times stronger than what the actual plastic deformation point is. So that's good, 113 times for a safety factor. Next, we're going to figure out how much that frame costs. So we just want to select the frame. So if we hover over it, you can see frame is highlighted. So that's what I need to right click and go to iProperties, then physical. And I'm in steel right now. I may have to click update. You may have to, but I don't because I've already been in steel. That's my mass. So I need to highlight that, Control C to copy that. And then I'll go to my spreadsheet and I can paste that, Control V to paste it in here. To find the frame cost, we do formulas again. So I say that's equal to, and I click this cell, and then I do the times, which is Shift 8, or that star, this cell. And now I need to see what the cost of that safety factor is. So if I click on this cell, then I do that equals the cost divided by, per is divided by the safety factor right over here. And so each unit of safety factor I have there is costing me $1.96. So you have a lot of different things on here. You have this cost per safety factor, you have the cost per pound, you have the total mass, you have ultimate tensile strength, you have just safety factors in general. You're going to need to use these and some combination of these to help answer the conclusion questions. There is no right or wrong answer. I just want you to think critically about this when you're trying to decide what is the best application for steel, titanium, or aluminum. All of these things come into play in some aspect or another, and that's up to you to decide how that's going to play out. Next, I need to show you how to actually change the frame itself so that we can change the other materials of titanium and aluminum. So if we go into the design and frame analysis, and then we right-click materials. So this is just adjusting the frame. We go to beam materials, and we're going to select all these. So I can hold the shift key down and click all these. So I'm holding the shift key down while I click these to select them. Then you click customize, and now we can change the material. So we'll go to titanium next, and then apply that, and now we are all set. So I've hit the X here. Now if I simulate this, let's double check what our load is, our gravity load. So right now I have it set to 1G. So you want to make sure you're double checking that so you know what your load is. Click simulate, get rid of that solver error, and it's always going to show you almost always displacement first. So do not put this number down here. You need to make sure that you are going into normal stresses and then do S max. So the S max 1G for titanium is 0.3877. So again, that's what I would record then on this one. I'd record that value. So you're going to need to make sure that you finish up all of the total effective weights, all the stresses, safety factors, and so on and so on. Once you have all this information, then you can do the analysis of the data through the conclusion questions. If you have any questions along the way trying to figure out how to get some of these values or make some of these adjustments, please ask me, but really make sure that when you are recording these normal stresses that those values make sense. They should be somewhere here in the tenths of a unit of a KSI. If it's not, you probably were in displacement, which means you're going to have to redo that one. All right, let's get to it.